Good morning, everyone. Today we're going to start our look at calculus, but before we can move into calculus proper, we need to do some work around the terminology that we are using. So in this case here, I'd like to introduce you to the idea of rates of change, which is really just a fancy way of saying gradient. The idea behind calculus is that we can use it to calculate the gradient at a particular point on any type of equation. All right, so normally when we're working with gradient, we've previously only been working with linear equations. So, your y equals mx plus c's of the world. But gradient is always something that we can talk about in terms of being something positive or being negative. So for example, I have a graph behind me, and obviously it starts at negative infinity and it goes all the way here to minus 2, goes to plus 1, and then it goes off to positive infinity. At some point on this graph though, I have positive gradient, I have negative gradient, and I have zero gradient. Not no gradient, zero gradient. So if I'm looking at the section of the graph that is here, would you say that is positive or negative gradient?
Positive.
Positive. So imagine it like a straight line. Right? If it was a straight line, would you say that line is positive or negative? Well, clearly it's positive. If you look at this section, it's also going to be positive. So we'll just say plus VE. Now, obviously because I'm changing colors, there's going to be a big hint that something's going to change. If I look at between minus 2 and plus 1, what would I say the gradient of that section is? If you imagine it as a straight line, yeah, it's going to be negative. Now, the important thing to also think about is, what about at exactly minus 2 and exactly plus 1? All right, if you were to draw a line that just touched it and nowhere else, what would the gradient of those lines be? They would actually be perfectly flat. They would be flat graphs. So they would have zero gradient. So the purple here have a gradient of 0. All right? Because at that point in time, the values aren't changing. So there are a couple of different concepts that we want to be talking about. First things first is constant. If something is constant, what does that mean it's not doing?
Sorry, sir, I didn't catch that.
If something is constant, what is it not doing?
Changing the gradient.
Yeah, it's not changing. So if something is constant, it means not changing. And this is an example. So constant, so if something has a constant rate of change, means the rate of change itself isn't changing. So the rate of change you could map as almost being a straight line. So you would, well, that's obviously unacceptable. I can't in good conscience leave that up there. Oh, that's marginally better. But if you were to look at the rate of change and you were to draw it as straight lines, it would be like that. Or it could be like that. All right? The gradient isn't changing. It's always the same length. Now, one of the other things that you're going to be expected to recognize is when I talk about things having a gradient, we're talking about m. And the formula that you guys might be familiar with for m is y2 minus y1 over x2 minus x1. The problem is, between then and now, you've learnt of this little thing called function notation. So the question for you is, how would I represent this in function notation? So, if I have a function f of x, and I want to know the distance between point A, or x, so at x equals A, and x equals B, I can end up writing this whole thing as f of B minus f of A divided by B minus A. So I'm basically taking the entire thing and rewriting it in function notation. And if I have to determine what the rate of change is using that formula, I am finding the average. The average rate of change. So if I pick any 2 points or any 2 values for x, and what I'm trying to do is I'm trying to find the gradient of the line that connects those points. And that is my average rate of change. Now, part of how they invented calculus was they came up with this process where, well, if I'm working on a line, and I've got just bring out the ruler. So let's do something simple. Let's do a parabola. If I wanted to talk about the average rate of change between the turning point, which we're going to say is at plus 1 minus 2. And I wanted to find the gradient between this point here, which we're going to say is 6, 4. And I wanted to find the gradient between those 2 points. I would have, so what is the gradient of the line that connects those 2 points? So what is the gradient of that line there in black? Well, you would use that formula that I've got behind me. So f of B, so it's 4 minus 2, because f of A is minus 2, and then 6 minus 1. So that's going to be 6 over 5. And that is the average rate of change between those 2 points. But if I pick a different point on the line, and this time I'm saying it is 4, 1, then I'm going to be working with a different set of values. And the gradient is indeed going to be different. Because it's a curved line, the gradient is always changing. But what if I keep going smaller and smaller and smaller, and I'm starting to worry about the gradient between, so this here would be, it would be 2, 1, negative 1.4. As I keep changing the gradient between the points, what is happening to the line that I'm making?
It's becoming shallower.
It's becoming shallower. And eventually what's going to happen, because I said this was the turning point before, what if I'm trying to find the distance, trying to find the gradient between, so 1, minus 2 and 1.001, minus 1.999, or however long you want to go for. And I could go even further and I could add more zeros and more nines onto it. So the gap between those 2 points becomes infinitesimally small. And in mathematics, when things are infinitesimally small, what do? We just call it 0 and we move on with our lives. All right? And this process allows us to get what is called the instantaneous rate of change. So the instantaneous rate of change. So if I was trying to find a gradient between 2 points, it might get to the point where my gradient is just, it could be 1, it could be, 0.01, it could be 0.021 or whatever. It could be really, really, really small. So you've got constant rate of change, you've got average rate of change, and you've got instantaneous rate of change. Where this leads us to is into calculus, which is the formalized study of rates of change. And what I want you to do, or what I'm going to show you, is a thing called differentiation by first principles. What I can do is, through this process, I can create an equation that tells me the gradient at any point along any curved line like this. So it'll tell me if things are 0. It will tell me if things are positive. It will tell me if things are negative. Because if I keep drawing these lines over time, they flatten out perfectly, but then they start going the other direction because they're now negative, and then they flatten out again. And then, so they flatten out and then they become positive again. So, positive, flat, negative, flat, positive again. So, for example, for f of x equals, let's do something like x squared plus 5x plus 4. Find the instantaneous rate of change at x equals 1. So when x equals 1, what is the instantaneous rate of change? So what we can do is go, well, okay. Yeah, all right, okay, good. I'm glad you know. So some people will already know this because you did extra study, you've read ahead in the book, etc. So Mubasha has already confirmed that the answer is 7. Cool. I agree. The answer is 7. But through the instantaneous rate of change process, what we need to do is we need to think about, well, we need to find a number that is infinitely close to 1, but not actually be 1. So we will then go, for example, so x is 1. So x1 is 1, and x2 will be 1.001. So what I now need to do is I now need to find y1 and y2. So that's x, this is f of x1 and f of x2. All right, so you get your calculator out for a little bit. So for example, when x is 1, 1 squared plus 1 squared plus 5 plus 4 is 10. And if I put in 1.001 into my calculator, this is why we can use function notation, because we can do this. And it makes our lives so much easier when we're trying to do these calculations. So for the record, average rate of change, you need to be able to do it by hand. Instantaneous rate of change, when the numbers are so small and fiddly, that is something that you definitely need your CAS for. So what I'm going to do is I'm going to define f of x is equal to x squared plus 5x plus 4. So if I just want f of x, cool. So f of 1 is 10, like we said. F of 1.001, let's get that as a decimal, 10.007001. So what I now need to do is I need to use my formula from above. F of b minus f of a divided by b minus a. So it's going to be 10.007001 minus 10, which is our original value, divided by 1.001 minus 1. So I'm gonna do that. So it's gonna be f 1.001 minus f of 1 divided by so your CAS you can just do this you can just do this with your CAS, and the answer is 7,000 over 7,000 over 1,000, or 7.001. So the answer that Mubasha gave us before was 7. Because what he's done is he has gotten the gap so small that it might as well be 0. Because if I was to go back and I was to repeat this process, and instead of it being 2 zeros, I'll put 7 zeros in. And I will repeat the whole process. Now I'll put my calculator into decimal, so it will automatically put it into decimal for me. And the calculator's like, yeah, it's 7.00000000000, etc. 0.01. That, yeah, it's basically 7. You're working with such an infinitely small set of answers that it might as well be 0. That is the actual answer if you express it as a fraction. But when you're thinking about the differences being that small, just round it. Where this becomes interesting is when you start saying, well, okay, let's just think about it in terms of, well, I have h. H might as well be 0. The distance between my point A and my point B is so small. What I can do is I can create a general equation that describes everything that's happening on that line. So I have 2 things that are important. I need to have a function, which is f of x. And in this case, we're going to use the same one that I used before. Now, what I'm going to do is I'm going to need to find another point. And what I'm going to do is I'm going to call that point x plus h. All right, just going to call it x plus h. So it's h units away from x. And don't worry about the h. We will deal with that momentarily. Now, if I go back and I use this formula that I have here before, and I use x and x plus h, I can create this new type of equation. All right, and it's called f dash x. Right? And this is the derivative. This is the gradient equation. So if I'm talking about f of x, x squared plus 5x plus 4, f dash x is the gradient equation for f of x. Now, I'm going to put in here, this is a concept called a limit, where the equation will repeat itself infinitely many times until h approaches 0. So that's all I'm saying. I'm just saying that h is going to be infinitely small. And then what I'm going to do is I'm going to write the actual formula that I need to write. F of x plus h minus f of x divided by x plus h minus x. Can I simplify that?
Yeah, x's cancel.
Yeah, so I've got x plus h minus x, those x's go away. So I'm left with f of x plus h minus f of x, all divided by h. What I now need to do is I now need to find out what is f of x plus h. So I'm going to need to find out, well, what is What is f of x plus h? I replace all the x's in here with x plus h. So what's that look like? Well, that's going to look like x plus h squared plus 5x plus h plus 4. And then you need to expand all of that. Then hopefully your rules are not too rusty. Five x plus 5h plus 4. So now what I'm going to do is I'm going to put this, because this is f of x plus h, into my original equation. And I'm going to put f of x in as well. So I have x squared plus 2xh plus h squared plus 5x plus 5h plus 4. And now I'm going to minus the original equation. All right, remember I'm minusing the original equation. So that means it's going to be minus x squared minus 5x minus 4. And that's all over h. And I still have my lim h approaches 0 in there. So now what I can do is I can go through and I can just cancel out everything that can be cancelled out. I've got an x squared and minusing an x squared. I've got a plus 5x and a minus 5x. I've got a plus 4 and a minus 4. So now what am I left with? So I've got lim h approaches 0, 2xh plus h squared plus 5h, all divided by h. I don't know about you, but I think I can simplify that. What is in every single term along the numerator, along the top? I've got a h.
H.
So I can factorize out a h. And then I can get rid of that one there. I can get rid of a squared and I can get rid of the h there. Then I've got a h divided by a h. So now I have f dash x equals lim h approaches 0. Oh, don't need that. 2x plus h plus 5. And then this is where I get rid of the h altogether. I just say assume h is 0. So it's the limit as h approaches 0, but now I'm just saying stuff it is 0. And what I'm left with is an equation that is f dash x equals 2x plus 5. And I now have an equation that describes the gradient at any point along my equation that I started with. And then, to prove a point, what is f dash 1? 2 times 1 is 2 plus 5 is 7. I have worked out the actual gradient for that point. So at that point, when x equals 1, the gradient is 7. because we have used differentiation by first principles. We have done all these different calculations for all the different lines that are coming closer and closer and closer to 1, to the point where it might as well just be 1. Not 1.000001 as I did up on the CAS before. It is just f of 1. Alright, this is called differentiation by first principles. This is going to be something that we are going to spend a little bit of time on, because you need to be able to do this by hand. Alright? There is a shortcut. However, you need to be able to do it by hand like this. Alright? That is one of the requirements as part of the SAC and the study design. The shortcut is a shortcut. The shortcut is so much quicker. Alright? I looked at the question before, and I'm sure that other people in this class who are familiar with the idea of calculus could go, oh, well, it's 7, because I know how to differentiate by rule. However, differentiating by rule doesn't always work. Especially when you get into different types of functions in year 11 and in year 12, when you are trying to do things like differentiate sine. Alright? It all kind of falls apart there. Or differentiating hyperbolas and truncuses. So, the work that we've got here covers chapters 16. So I've literally just sped through all of chapter 16. I expect you to read all of chapter 16. If you feel like doing the questions is going to help you understand the concepts better, please do that. This differentiation by first principles is in chapter 17A. Alright. I will put the notes up. I will put the textbooks up for you as well. Alright, so read through chapter 16, having a go at questions from 17A. If you feel like you need to practice the skills from chapter 16, please do. Won't be mad if you need to.